Hello, so in this session we will continue our discussion about the four-part mechanism, and we said that the Grashof law says that if the shortest link plus the longest link in a four-part mechanism is less than or equal to the summation of the other two links, then you should have a link that is capable of full revolution. Now I will do this in practice, the four scenarios at which we have different cases for the shortest plus the longest is less than P plus Q. We can get a crank rocker mechanism, double crank mechanism, and double rocker mechanism. So part all right. So I will draw the in front plane. Okay, I choose a slot. Okay, center, circles, add dimension. I will be choosing this to 150. This is equal to 10, and this is equal to 20. Right? I will add relation to this circle and this circle, and they are equal. Now it's fully defined. I extrude by 5 millimeters, and that's it. So this is the first part, so I can save it. I'll be saving it on the desktop. For mechanism. So this is the first part. I will edit the second part. It is 180. Okay. And save as part 2. Okay. And the shortest link is, can edit. I'll be choosing it to be 100. Then save as part 3. So I've been choosing 250, 180, and 100. And the shortest link is 100, and the largest link is 250. So in total, we get 350, which is less than the summation of the other two links. If I choose the 180 two times, then I get 360. All right. So now I will go into assembly. I can start from this, or I can start with a new platform and assembly. So either start from this or create a new assembly. Both are correct. So I'll browse for the materials. So the first part, okay, this is the first part. By default, it will be fixed. Insert component, you can fix this. This is the second part. Okay, I have two items of it, and then this is the third part, the shortest link. All right, great. So by default, because I inserted this component part 1, it will be fixed. Now I will add mates among all the shafts or the components. So this one with this one, mate. Okay. This face with this face. It will be, as you can see, coincident. Okay, so you can move this part, right? now you have this shortest link. So in the first scenario, I will be attaching the shortest link um, to the ground, and you know, if we attach the shortest link adjacent to the fixed link, we should achieve a crank-rocker mechanism. Okay, great. Coincident. And at the final stage, we can have only concentric mate between those last two items. Okay, so you have this mechanism. So in this case, the shortest link is attached to the longest link or to the ground. So you should have a crank rocker mechanism. So I mean by crank, one of the links will have a complete revolution and the other one is a rocker. It oscillates. Now I go into motion study. In the motion study, you should have motion analysis as well, animation and motion analysis. If need to be added, you go to the options, at this gear, add ends, and you should select the Solidworks motion, this one. Okay, now you add motor. Okay, you add motor to this link. Okay, so you should choose the second link. Okay, this one. I will add this to be 15 RPM, and that's it. So now you can run the animation. That's fine. Now, in order to perform motion analysis, okay, you can choose this joint and create motion plot, and you can see the trace path. Okay, I'm not interested in this phase, only on this edge. All right, great. All right, so you can see this is a rocker. Okay, okay. Now I want to add for this joint as well motion plot. Okay, and then I can see this one. All right, you can extend the period of simulation like into 10 seconds. So this is called a crank rocker mechanism. All right. Okay, now I want to simulate, for instance, let's say so this is a double crank mechanism. Let's simulate the third scenario, which is the shortest link must be opposite to the fixed link. Okay, so I will choose this item, I will float it. Okay, and I will fix this one, the opposite of the shortest link, so I can obtain a double rocker mechanism. So I will fix this item, this component, second one, fix. Okay. Now we can simulate this one. Okay. All right, and you can as well obtain the motion plot or the path, create motion for this joint, displacement and trace path. That's fine. Okay, and run. So as you can see, this is a double rocker mechanism at which you have two links which are oscillating. Now, as you can see, the motor is fixed to this joint. I didn't change the location of this motor. Instead, you can put the motor at this joint, and you should be careful about the rotation of the motor. So you can, for instance, delete the motor, okay, add a motor to this joint, and make sure to choose this one because this will be moving, okay. And here you shouldn't have constant speed one, you should have oscillating one, and you should define the degree based on the calculation and based on the link lengths. Let me choose, say, 45. This is 0.1 hertz oscillations per second. Okay, and run. Okay, so you should perform some calculations in order to have adequate analysis based from the course of mechanisms.